Okay, so I think it's now time to start. We are already 50 participants. This number will certainly increase. However, we have 3 discussion sessions this afternoon, about 40 minutes each. The first one will be led by Tetiana Galatiuk and Francesco Pederiva. This will be mainly about nuclear physics and what nuclear physics can tell when we extrapolate at densities higher than saturation density in nuclei. And then after we'll go more on neutron star observations with discussion led by Anna Watts and Nanda Rea. And finally, we will discuss more about gravitational waves and simulations, discussion that will be led by Tim Dietrich and David Radice. So now I leave the floor for the first discussion. And as I said before, I'll check the chat and I may interrupt some time just to control about the time. But except from that, I just leave you the floor. Thank you very much, Francesco and Tetiana.
Okay, thank you, Jerome. Thank you for your inviting me here to this workshop. It's always a pleasure to be able to lead a discussion in some sense, because especially because I think there is a need of some discussion in the subject of say nuclear physics in neutron stars. The title doesn't say much, but I would say microscopic inputs for the physics of neutron stars. And what I am meaning here is that of course, the details, we tend to forget that the details of nuclear structure and nuclear dynamics, both of them, are very pervasive in the phenomenology of neutron stars. I mean, sometimes we tend to imagine that the microscopic scale is not sufficiently under control, and we tend to forget the fact that, of course, the structure of the neutron star, in some sense, would be completely determined if we were able to go in a precise and detailed way from the nuclear interaction to the equational state. By nuclear, I mean I'm not assuming a two-body only structure for the interaction. I mean, nuclear means that you have to put whatever is needed, and this is exactly the point to some extent. I mean, the big problem here is that at a certain point we keep saying, well, we should solve the problem completely ab initio, and then we might in principle be able to make predictions. What does it mean, solving the problem completely ab initio? And here, this is an interesting point to debate, okay? Because if you listen to a certain bunch of people, they say, okay, you would have to solve QCD for doing that. And okay, that's probably too much, at least up to a certain density. On the other hand, while it seems that the description of the nuclear interaction is quite successful up to a certain, even for reasonably large nuclei at this stage, the step that brings you to the equational state is still very high, and this has been there for several decades. It's not something new. Of course, nuclear physics enters heavily in the study of the details of the crust. For instance, one thinks of the outer crust. There is all this interesting work. There is also this recent. I'm quoting here just for as an example a recent paper by Nicolas that sort of revisits all the determination of the layering of the outer crust. And that is a nice example of some sort of, I would say, standard quotation mark nuclear physics, in the sense that there is a clear connection also with the experimental data on the binding energies and so on, which is somehow interesting. And of course, there is the story of the pasta phases that we all know. But I mean, pasta, what is the pasta exactly? What is the pasta exactly? I mean, the symmetry breaking is a very nice way of imagining this kind of phase. But what you have probably is more like what you would see in a phase transition from a vapor to a liquid, which, by the way, is there in many other systems. I mean, if you take some helium-3 and you sort of decompress it at very low temperature, what you would get at a certain point is a phase in which you start having bubbles and you start having droplets and you start having a number of strange structures that just appear when you have a transition to what you would call in that context an exotic phase. So again, there are many things here that are still pretty much. I would say that there's been a lot of studying, but we have no certainty. And here I mentioned a couple of papers, also the one from Jerome, Alessandro, Sanjay, Luke, and also, I mean, there is all the work by Horowitz and company that worked on this subject for a long time, and also giving some very interesting insight. I mean, this concept of pasta is maybe oversimplified in some way. There is the issue of superconductivity. There's been a lot of work about the S-wave superconductivity, but what about P-wave? I've been searching literature a lot, but there is not much. That might be an important issue, and it's just up in the air, and there is not much going on there. Not to mention the inner core. I mean, the inner core, we are sort of imagining several things, and every time I say that, unfortunately, we cannot go and dig and see what's there. And I would say that the story of hyperons is not over yet, not completely, at the very least. There's less and less talking about condensates, but that was that is something that maybe should be also reviewed in some way. The confinement, also there is not the fact that now we know that there is a constraint on the mass. I mean, as a sort of hindered, I would say, the discussion about all these phase transitions, because phase transitions mean softening in the equational state. We have to remember that. But as we saw with hyperons, I mean, there is room for phase transitions that still might satisfy the constraints on the mass. But say the question that I do in the end is, does it actually someone still care about that? I mean, I would be happy to know, especially by colleagues working in other branches. I mean, the gravitational wave, for instance, frames, if they still care about the details of what's going on in the neutron star cores, which is a great problem in nuclear physics, but maybe is no longer so crucial, so critical. I mean, that's what I perceive a little bit. And last but not least, and this just, I mean, I'm not pretending that I'm exhausting, I'm just throwing there a few examples. Neutrino physics. Neutrino physics in relation to the detailed nuclear dynamics, for instance. So, just a couple, very quickly, a couple of examples. This is a very recent paper by Hakim and his group, in which they propose a parameterization of the equation of state, and they discuss, and of course, this parameterization is done using a whole host of theoretical and observational constraints. And I just want to make a point here. You see that while I would say that up to a substantial fraction of the saturation density, the situation is reasonably understood. What happens even at saturation density and above is still very uncertain. And of course, what is the attitude here? The attitude is to say, okay, let's provide some, let's look at constraints, but in some sense, my feeling is that we are giving up completely on this idea of being able of making predictions. Making predictions means Akmal-Pandaripandaraven alike. Let's say it's let me say a blasphemy, but where the curve was sort of one. Of course, we know that that's not easy to reach. But should we really give up on that? I mean, this is a question. I'm not. This is just a question that I want to drop there for your consideration. And the same thing. This is just another similar example that concerns hyperons, and I am very fond of this problem. But also here, I mean, of course, there is the lack of information also for what concerns the experimental sides at the level of the understanding of the nucleon-hyperon interaction, hyperon-hyperon interaction, and so on. And so the situation is even more smoky in some sense, because you can write down a Lagrangian and just work with that, but giving constraints on not just on the neutron star side, but also on the microscopic side is very difficult. So there are several models, there are several possibilities. You can be more or less phenomenological. And of course, you have certain constraints, like the constraints of the maximum mass that you have to respect. But what are we learning here? What are we really learning here? I mean, is there any chance that we can be able to make predictions at a certain point? Should we just give up on that? Should we insist on that? Of course, as I say, as I repeat, there is a certain amount of information that is coming out, but that also has to come from experiments in the lab, which is important. Okay, I'm done. I think I will leave the floor to Tatiana.
Yes, thanks. I will try to share the screen here. Good. Okay, yes, thanks. I just heard the mentioning of the experiments in the lab, so I will be down to the earth now, not looking so much into the star, and will not like to occupy too much time. Still, also would like to pose the question, what laboratory experiments can tell us about extreme environments in the universe? And maybe also this question from the previous slide, do we still care, and do we still need to learn something from the experiments in the lab? So what I brought here on this transparency is actually our approach by using high energy heavy ions and also proton-proton reactions, try to answer a couple of questions which are also of relevance when we discuss the matter formed in the neutron star merger events or matter which is existing in the inner part of the neutron stars. So what we try to do with our heavy ion experiments is to learn about the QCD phase structure at different temperatures and also different baryon chemical potentials or just the density of the matter. Let me focus on this particular range of the QCD phase diagram. And of course, in the earlier days, we try to connect all what we do in the laboratory to the neutron stars themselves. But of course, it was not an easy task because neutron stars are the cold object. And if we collide heavy ions in the laboratory, we definitely compress, but at the same time, we also hit the nuclear matter. So now with the neutron star merger event being detected in gravitational, also in the electromagnetic spectrum, it became evident, at least from the model calculations, that temperatures that are occurred in the course of the neutron star merger events is reaching up to, let's say, 80 MeV. And this, of course, brings this nice connection to the experiments which we can do in the laboratory. And in this particular range on the QCD phase diagram, despite the fact that we might be still away from the true deconfinement and chiral phase transition, we can learn a lot about the microscopic structure of the matter created here. And just an example, I show you here a recent calculation from the parity doublet model, but also including FRG methods, and also all the calculations which predict substantial depletion of the chiral condensate in this particular region on the QCD phase diagram. And this, of course, influence all the observables that one can see in the heavy ion reaction. So now, just to confirm to what I said before, here I show you calculations of one of the models. There are many of them exist. This diagram shows the temperature as a function of density, which compares maximum temperature at the given density, or other way around, maximum density at the given temperature for the binary neutron star merger event. And here the set that has been used for the calculation together with the trajectory of the heavy ion reaction. And here I show you two examples, one for 1.2 GeV per nucleon, or 2 GeV in the center of mass energy, and another trajectory which is of the order of 600 MeV in the collision energy. And here one can nicely see that indeed some part of the matter which is produced in the neutron star merger event could be indeed addressed in the laboratory experiments to really learn about microscopic properties of this matter. Yeah, what can we do? I did not show the figures here, what we really experimental results, but there are just few examples here, recent examples of what has been done. What we can do from the laboratory experiments is to constrain the symmetry energy by looking at the different observables like production of the particles, or which becomes more and more valuable, is to look for the anisotropic azimuthal anisotropy of the particles which are produced in the reaction. And here I would like to mention that indeed this is like a long history of all that physics observables. But important thing to mention that also in the heavy ion reactions, we are getting better and better instruments to look at the heavy ion reaction. So now the precision of the experimental data reaches very high quality, and it would be essential to involve now various observables, not only one, but here I brought you 3 of them, and then to describe all these observables in the coherent way. So from the hyperon-nucleon or hyperon even nucleon-nucleon, so 3-body interactions, we are not yet far to do the 3-body interactions, but there are new data coming up from the LHC experiment ALICE, also measuring with the high accuracy hyperon-nucleon interactions that might be relevant also for modeling of the neutron stars or also merger events. And then last but not least, what we can also do in the lab is to look for the modifications of the spectral functions of the particles, either mesons or baryons. And for that, we use either virtual photons or dileptons, or we can also look at the objects like baryons, for example, what happens to the delta at temperature of 50 MeV and 2 times of the normal nuclear matter density. And this, of course, can also bring into the contact what has been discussed in the previous contribution. So maybe one last point to mention is that we often now discuss in the view of the heavy ion physics about the role of the meson cloud, because if one would view the nucleon as the quark core with the surrounded by the meson cloud, by compressing matter to say 2-3 times of the normal nuclear matter density, clearly will lead to the fact that the meson clouds will overlap with among each other, and this percolation of the meson clouds would also lead to the possibility of the quark traveling much more easily in the system that has been created. And in some of the recent papers, there are also discussion about the separation between soft and hard deconfinement. And of course, this type of the scenarios might also be interesting in the modeling of the neutron star, inside of the neutron stars, or also merger type of the events. And yes, with that, I basically open floor for questions and discussions.
Okay, thank you very much, Francesco and Tetiana. So, well, I think you raised many very interesting points. I'll leave the floor for discussions. There's also a discussion in the chat on a different thing. I don't know.
May I ask?
Yes.
Yes. Yeah. Today, I repeat one simple question. I have some non-accelerator experiment in which I have measured the dependence of the strong nuclear force interaction on the distance between nucleons. In my quest connect with who has any theoretical elaboration this phenomena. Yeah.
So do you mean so your question is associated with the fact that as the density increases, the nucleons get closer and closer? Is that what you mean, or?
I mean, we measure the dependence of the strong nuclear force on the distance between nuclears in deuterium nucleus. Yeah,
So
understand.
maybe this is more a question from Francesco, no?
Yeah. Thank you.
The problem is that if you do that in deuterium, that's definitely interesting and might be an interesting piece of information. The problem is that a big deal of what's going on at the level of the equation of state is due to three nucleon forces. And this is of course three and more. Who knows? I mean, I'm saying three, but could be more. I mean, this opens again a world of questions in some sense. But this is exactly one of the problems that we have, because it's when we have an interaction, an Hamiltonian that describes reasonably nuclei, and you port it to the study of the equation of states, you find some contradiction. If you try to fix the Hamiltonian to describe the equation of state and you go back, you find some, and you try to study nuclei, you have a contradiction. So the physics is the same. The physics has to be exactly the same. I mean, there is nothing that tells you that what happens in neutron matter and nuclear matter is different from what happens in nuclei in some sense from the point of view of interaction. But we don't understand the interaction. That's my point. I mean, the two-body interaction is a piece of that, but it's not sufficient.
Have you any theoretical explanation this effect? No?
No.
Okay.
Well, right now.
Maybe that's I mean a pretty very interesting question, but I mean maybe we should just I mean let you discuss more privately about that. Yeah. I think.
I'm sorry.
In the chat, there is a very long discussion in the chat, and maybe there is also something that people could comment about it. Andrew started the discussion about the P gap that could be inferred from the cooling of case A. And Prakash backed him. So now there's a very interesting question about whether we really need to make a hard calculation from ab initio nuclear models, or can we just rely on neutron stars to tell us about what's the pairing gap? So I don't know who wants to defend his viewpoint.
I will be very thankful if some send me such elaboration. My name is Plikhanov, and I'm in a list of participants.
Good. Yeah, we'll make you in contact with Francesco, no problem. So Prakash, you were starting.
Yeah, I may comment a little on it. Well, there is theory and there is data, mostly very sparse data from neutron stars. Not terribly accurate, but something to go by. The theory is pretty uncertain in its predictions. I'm looking at a figure that we had published a long time ago in Stellar Superfluids. And when I say we, which is really Danny Page, and also the group from Yoffe Institute led by, I keep forgetting his name, he's one of my great friends. Anyway, the Yoffe Institute. And the theory is pretty uncertain in the following sense. The density, which Jerome asked, at which the peak occurs ranges from 1.2 to 2. Fermi minus 1. That's the peak at which the peak occurs for the TC. So that is uncertain. The magnitude is also a bit uncertain, but not as much as the density at which it occurs itself. Well, the magnitude varies by a factor of 1 to 2 for the TC, in theory, that is. When analyzing the data, the Yoffe group and our group, Jim Larimer, I, Andrew, and Danny, principally. We explored all sorts of possibilities. So it was not so much the density that mattered, although it had some effect, but it was the value of the critical temperature itself, for which I think both the Yaffe group and our group independently came to the same conclusion that the critical temperature was around 0.5 times 10 to the 9 K. So that's the best we can say at this point in time. Your question, Jerome, about should we rely on one or the other? That is a bad way to go. We have to use both. Theory is a theory and the data is data. So whatever we can get, we should use from the stars, because at those densities, laboratories cannot help. In laboratory nuclei, it is just the S-wave pairing. And as we all know, the pairing energy is a real fact in life. So I think, Dima, thank you, somebody. Winho, of course. Heinke and Winho were extraordinarily helpful in communicating data with us about Casey, Peter Sterling and Dima, of course. So independently, it was amazing that independently we arrived at the same conclusion, and the papers were published almost a week apart. So, and there was some question in the chat that I noticed that Pavlo and company were saying that it did not decrease that much. And I think Winho and Craig Heinke, remeasured it. Amazingly, all 5 detectors on Chandra were used for this purpose. And it was not as large as originally thought, the rate of decrease, but the decrease still persisted. I hope Winho can attest to that, because he's in the chat. So that's about how much I have to say. But it's a hard subject. The nucleon, see, there is one thing about nucleon interactions in the core, but superfluidity is on top of it. And that depends on the methodology by which people compute it. What has not been done in the old Bethe style is for people to compute the same thing, the same object, using the same interactions, and see what the differences is. In other words, theorists check each other. I think that habit must be restored. I very strongly believe it, because I have interacted with Bethe. That was a very good practice. But now people do their own thing, and we get this in Darmstadt, we get this in Argonne, we get this in Los Alamos, and there is no common ground. So I think that is they should all exhibit that it began like that with Clark, if I remember right, in Washington State, but it somehow got diverted away. So I think it is a very important subject. Thank you.
If I can make a very short comment, I mean, I have seen several papers about the S-wave gap done this way, in which you have substantial comparisons of different theories, of different methodologies.
Exactly.
And when the problem gets harder, I mean, I'm talking about the P-wave gap, I mean, it looks like people just try to
I'm looking at S-wave, even that has a little better convergence than P-wave, the S-wave. Not as much variation, but S-wave is low density. P-wave is high density, and for cooling of neutron stars, it's the P-wave that matters.
Yes, yes, exactly, yes. Oh, there was someone asking about what part of neutrino physics is relevant. I was thinking about essentially, for instance, the determination of cross sections with neutron nuclear matter. It's maybe not relevant in the neutron star, say, per se, because the mean free paths are typically of the order of the star dimension, of larger. But it might become,
when neutrinos are trapped, it is important.
Yes, it is important, but let's say
even for the equation of state.
Important when you have, for instance, neutron star mergers in which you have situations in which the neutrino physics becomes extremely relevant. That's also a subject that people, I mean, no, it's discussed, but it's very uncertain again. There are several models, several results, and no, this point that Prakash rose, the fact that there is a need of comparison of data and discussion in that sense, I think it's very important. And there are several examples.
Okay, I would like to ask before the session closes a question to Tetiana about the heavy ion collisions and what she presented. So my question is somehow, is there any clear connections between the properties that you measure and the properties of the equational state that we need to predict neutron star physics? May you elaborate a little bit more, because you show a comparison between these two objects?
So maybe I will just use directly example of emissivity of the matter, which we create in heavy ion reactions, so related to virtual photon or dileptons, right? So there we can basically, in the theory independent way, measure the temperature of the system that is created. And then we still need the model in order to connect this temperature dependent spectral function of the dileptons that we measure to the density that is created in the system. But then directly from the measured spectra, we can establish the temperature of the systems that has been created. So then in addition to that, we can look to the flow observables, and meanwhile we can also measure up to order of 6 azimuthal anisotropy of the particles. And there we know that also, now very modern applications of the IE methods to look at comparison of this flow observable to establish the equation of state, mainly to relate or extract the compressibility of the matter which is created. So, and these measures become more and more precise. But again, they do rely on the model calculations. So what we can really do in more model independent way is to extract the temperature of the system with the relation to the model calculation. We can relate this to the density of the matter, and there we have a good measure. We are working now to establish the corridor of the errors for the density. Temperature, as I said, is measurable. And this is how we try to at least establish what we see in the heavy ion reaction, or connect this to what one would see in the some part of the neutron star merger event. As I said, temperature is the part of it. Yeah.
Okay, thank you very much. I see that there are, many questions. In fact, we should have dedicated much more time for this discussion. I think that once we will be physically in Trento, we will dedicate more time. But since this is a virtual workshop, we decided that maybe we have to bind it into finite time. So I'd like to thank Tetiana and Federico very much for leading this first session about nuclear physics. And now I'd like to invite Anna Watts and Nanda Rea for the second part of the session, the discussion session about observations. Hello, Anna, and hello, Nanda.
Hello, Jerome. Hi.
Okay, so I leave you the floor. It's your turn.
Nanda has the slides to share, I think.
Okay, good.
Okay, I share?
Yeah.
Do you want me to share? Okay. Give me a second. Here they are. Share. Does it work?
Perfect.
Present. Anna, do you see it?
Yes, I see it. Excellent. Okay. So we're going to do this a little bit informally split between the two of us. So Nanda, please jump in if you want to add things. So we've kind of put together a list of, just to start with, a few things that were some discussed during the meeting, some not discussed during the meeting that we want to kind of put forward as potential topics for discussion. And then we'll look in a little bit more detail at what's coming kind of with current and future missions that are planned, basically in terms of expected observational constraints on the electromagnetic side. So one of the things I think that was fairly clear is that, you know, we need to understand both statistical errors and also systematic errors when we're trying to put our measurements together, and also trying to compare them and compare the different techniques. So just as an example, Nanda's put together this nice figure showing, you know, the nice J below 30 result. If you go out to the 3 sigma statistical error, basically it still covers an awful lot of parameter space. Okay, so we still have quite a long way to go to make some of these measurements rather tighter. We do have modeling assumptions basically that go into a lot of the techniques, maybe not so much the radio mass measurements, which are based on, you know, very well-founded theory. But the other techniques, basically there are modeling uncertainties in there. There are potential systematic errors between the different techniques, and that's perhaps a little bit harder to get a handle on, but it's something we do need to look at. So in principle, the multi-messenger analysis that we're doing, combining, you know, gravitational wave, radio, X-ray observations, it's great because they're complementary. We can put them all together and make things a lot tighter. But it's also, I think, going to be important to treat those populations separately. You know, what would we get from gravitational waves alone? What would we get from X-rays alone? Basically putting these things together and actually comparing the two, because that will let us get a handle, I think, on systematic errors and modeling assumptions between the different techniques. So once we have enough measurements, we should be able to do that very well as well. And Andrew touched on this a little bit in his talk yesterday, that so far things are not noticeably incompatible, but that's probably because our measurements need to get a little bit tighter. An intermediate radius would seem to satisfy all of the constraints within the statistical errors at the moment, but perhaps tensions will start to arise as we get more measurements. Nanda, do you want to add anything on this one?
No, I think you just covered everything perfectly. Yeah. Go ahead. Next one.
Yep.
Okay. Let's see if I can manage. No, I can't. No. Yes. Okay. In the next one, we thought to just touch a bit what was discussed yesterday too about the cooling, which is indeed a very good tool to have constraint on many parameters, different parameters concerning the neutron stars in general. There are different, of course, this is something which the things that we wanted to point out, it's mainly the difficulties and the systematics that this has to then actually derive meaningful parameters and meaningful error on the parameters. And those are in several things are rather big, like X-ray cooling of low mass X-ray binaries. That is something that many people worked on, and it's a very, very well-studied way to somehow constrain equation of states and crustal properties of neutron stars. Of course, it has one of the list of systematics and assumption that you have is that you're never sure that you're not accreting. So all the temperature you derive in quiescence, you rely on the fact, I don't see statistically a power law that I might not be accreting. This is sometimes the data are not good enough to actually tell this with the big statistics behind. Cooling of isolated neutron star. This is one of the plots we are producing for a new work we are doing. But there are many groups doing this, many groups trying to somehow model the population of thermal emitting neutron stars, or let's say of neutron star with a thermal emission. And this has many difficulties. First, magnetic fields. Many of those has pretty strong magnetic field, which everything above 10 to the 12 is actually pretty strong. And there are a lot of physics that we don't know on such fields, and we assume for the cooling, like Neutrino emissivities, for example. Other things are more observational side. So many of those sources, the temperature of those sources, especially the one which have a strong non-thermal component, which are most of the young population of those, actually they are derived by fitting the thermal and non-thermal emission. Those two things in the fittings in the X-ray data are very correlated. and very correlated with NH that you have, which can also have different assumption behind of the abundances that you have. So actually you can have sometimes, if your data are not extremely good or your blackbody component is not extremely strong, you might have a huge systematic in there only depending on how in your spectral fitting you actually derive your black hole luminosity, which might vary by a factor of 2 or 3, depending on the NH you assume. So this is another problem. And there are many others, of course, which somehow is indeed a very good and a very promising tool, but we still have to, in all of the different places, be able to handle properly the systematics and the assumptions and the problems that we have in deriving the parameters, somehow telling a number for crustal impurities or equation of state constraint that do have a real constraint behind and not a very big systematic error associated. X-ray burst spectroscopy is also another way. I will speak about this in a second when mentioning Athena, which is actually something that will probably provide a lot in this respect. One of the things that we actually, while discussing today, we realized that in these 4 days, nobody really mentioned or really studied or proposed or worked on something related with magnetic fields. So magnetic fields were not really considered in this not deeply in this small meeting. Of course, one cannot really study everything and speak about everything, but indeed are something which are has ubiquitous presence. A magnetic field of 10 to the 8, we decide that we ignore it, but it's 10 to the 8. It's still a strong magnetic field, not speaking about magnetars or stuff like this. So this is something that might have huge influences on whatever we derive, because there is a lot of modeling and assumptions and something we don't really know yet behind. Do you want to add something, Anna? No. Are there any, if you have questions or comments, this is a discussion, just jump in. Just tell, also because I don't read the chat because I'm sharing the screen, so I don't know if there are comments or anything, just raise your hand. Yeah.
I'll read the chat for you if there is any question. On your question about magnetic fields, I think the answer is just lack of time, but yeah, I don't think there is any deep reason.
I imagine. One thing that I wanted to mention that it comes, maybe I forgot, it comes a bit from this plot, which is not final, so we are adding stuff. I don't want really to enter in this, is that I think that we are starting to see appearing many pulsars too cold to be true somehow, which might somehow go toward the fact that of Urca processes and fast neutrino cooling and these kind of things, that might be actually something that in some radio pulsars, X-ray bright radio pulsars, start to be observed in more than one. That's not all of them, of course, but in some of them. Okay, that's it. And next slide, if I can. Okay, here, one thing that we wanted somehow to put a bit in clear, there might be something missing. We did this together in the last 24 hours. So if there is something missing or something up, please tell, and we just revise it. So one thing that we wanted to somehow to show is from where measurement comes and which are, at least in our opinion, those which we label as green, those which are somehow with the least systematics or easiest, which is not easy at all. The one with a bit more are in orange, and places where actually there is, to our knowledge, yet not really a way for measure such parameters. And as you see, there are many things that can indeed be measured, both from equation of state side and from composition of atmospheres, of the crust, of impurity fractions and stuff like this, can be measured by different techniques, which of course are complementary and independent and can, as Anna was explaining just at the first slide, are very good to be to work together and try to use them all to give some more strong constraints, of course. Okay, we'll not get into detail of this, but if there are questions, just please tell. Anna, do you want to comment on this?
I guess one question I will have for the gravitational wave people is, would you classify the measurement of tidal deformability within spiral templates as green or slightly orange? So that's one question to come later.
Okay, I don't know if they want to answer it right now, somebody, or
this can come in the next session as well.
Next session. Okay, that's fine. This is yours. Go ahead.
Okay, so basically, coming on to the kind of next generation images, I'll just say a few words about where we go with pulse profile modeling. So the technique that NICER is using, well, we take advantage, we're doing basically spectral modeling, but taking advantage of the rotation of the star as well. So NICER is at least going to be online for a little bit longer. We've got 4 to 5 new measurements coming for that star, including a very, very tight measurement for a star with a very well-known 1.4 solar mass. So we have a mass constraint from radio. We've got updates to the 2 sources we've already done in progress. We have a much larger data set for 0030. We actually already have more data on 0740 to come as well, plus improved background modeling for that source to be done. I think the interaction with pulsar astrophysics is important in terms of our choices of surface pattern parameterizations that we look at. And that's been something that's been really interesting to see, but it kind of loops us back towards magnetic fields slightly as well. Because the range, we take a fairly ambivalent approach to what kind of patterns we allow, and it may well be at some point our pulsar astrophysics colleagues try and cut that down and restrict the range of surface patterns that we can consider for the hotspots. I will say NICER has NASA senior review later this year that will determine whether or not the mission gets extended. So Andrew said he wanted to put lots more NICERs on the International Space Station. You don't have to put lots more on, but please let us just keep the one that we have. So write lots of papers, please, with the results. And do nice things with them, and then we can make the case to NASA for an extension, basically for the mission. In terms of what is coming in the next few years, XPay is definitely coming. So this will be the first X-ray polarimeter. So we can see if polarimetry works to give us geometric constraints, for example, on accreting millisecond pulsars, and that will be very, very valuable for pulse profile modeling for the accreting and bursting neutron stars, which we want to do because they rotate in principle faster. So they should give us tighter constraints for pulse profile modeling. And the other lovely thing about the accreting stars is that we have, for example, SAXS J1808, which we can do burst spectroscopy, we can do burst oscillation pulse profile modeling, and also accretion powered pulsation pulse profile modeling. So we can try 3 different techniques, maybe also things to do with the accretion disk, kilohertz QPOs, and so on, put all of these things together and cross-check our techniques on a single star, which I think will be really valuable. We already mentioned this basically a couple of days ago. Observing strategy for this will be much more challenging. NICER has 1 class of sources it's looking at, and it's a core part of the mission. The large observatories that may come, like EXTP and StrobeX, will have many other things to do with their time as well. So we need to think quite carefully about how exactly we're going to do that. Okay.
Great. Questions? No. Okay.
Well, I think we can take the question at the end of your presentation, maybe. As you prefer.
It's as you prefer. You're the chair. Okay, let's do it.
Go. Yes.
Okay. So a brief mention about Athena. Athena, it's at the moment close to delivering its red book, that in ESA terms means starting construction. So freezing somehow the capability of the instrument. This will be frozen at the end of next year. As you have heard in the meeting, maybe a couple of times, it's a very powerful instrument. It has, you see the 2 instruments on top. One is the wide field imager, which you see the effective area compared to XMM, for example, or Chandra. And the good thing is also the wide field of view. So this is perfect with a big effective area, perfect, for example, to catch type 1 X-ray burst, to catch transient of all kind, with very big statistics. To give you an example, on top, you see some simulation with only 70 seconds of exposure of an Athena wide field imager of the iron lines shifted for 2 different frequencies, rotational frequencies of during a type 1 burst. So this is 70 seconds. It's for somebody that is used to XMM, Chandra, which are big instruments, it's really fantastic to be able to have such a resolution and statistic in so small exposure time. And so this means that many of the works related to accreting neutron stars, especially those that do need to catch transient events like type 1 X-ray burst or outburst of any kind, this is the perfect instrument to do that if you need spectral resolutions too. Otherwise, the XTP is fantastic for this too. Iron lines also, it's a very strong point of Athena, where in this case, this is just some simulations of some iron lines from the inner orbit of an accreting neutron stars, that if measured simultaneous with kilohertz QPO, that possibly EXTP can give also, might give constraints on let's say an upper limit on the radio, might give constraints on the inner disk radio close to the neutron star in this accreting system. Other important points that Athena will cover, there are many more, but let's say those are the ones that are the most important and probable one that will happen, are of course spectral modeling of isolated system and quiescent low mass X-ray binary, everything which is connected to finding faint sources which had cooled down. Athena will be perfect, especially if you search for lines, atmospheric lines, cyclotron lines, in case, for example, of strong magnetic field ones. This is going to be extremely important and extreme breakthrough of Athena. Similarly to what NISR does, this is the plot that you see below. Athena can also somehow do pulse profile modeling. Of course, it will not have the capability of this long-term monitoring of the source that NISR can, because it is a general instrument like XMM is, for example, not dedicated to this. But still, if you compare the limits that 100 kilosecond XMM or 100 kilosecond of Athena observation in the profile modeling of this millisecond pulsar can give you, you can see the colored region and the red one, which is the 3 sigma limits that Athena might give you. So with 100 kilosecond, which is a reasonable exposure time. So in this sense, Athena is also a very good instrument for similar study that NISR can do with this kind of millisecond pulsars. Next slide, just to mention, of course, we have to mention SKA. SKA have, there is a very nice paper actually written by Anna, very nice, about what SKA can do to probe equation of state. We just picked up one because it's probably the most interesting one, at least to my view, that which is measuring the moment of inertia of the in the double pulsar system. And this is something that has been many years that many people are waiting for this kind of measurements. They are not easy. They are very complicated measurements, because when you go in the timing residual and search for such small effect and detail, you have to be sure to control all the other. And in the others are, for example, even the gravitational potential, the movement in the gravitational of the galaxy, or stuff of this kind that that do somehow add a systematic error in your timing analysis and make such that the baseline in which you want to do your measurement might be longer than what you hope for. So this is a very nice paper that was from last year from Hu, Kramer, and many other people that work on these sources since decades, where you can see, for example, in the plot below, you can see the error on the measurement of the moment of inertia that will come from the campaign of the current data plus 2 Meerkat campaign and a SKA campaign, which are really very, very tiny, of the level of 10% or so. And on top of this, of course, I will be all the results that will come from the fact of having a fantastic radio timing machine, very large field of view that will definitely discover at least 100 more double neutron star systems, which means also Shapiro delays measurements, which means many other masses for neutron star that can give, can somehow add to the statistics of masses that we have now. In this more high mass neutron star, of course, they will find, for example, yes, they might find very fast pulsars, which, as you know, are also a very good constraint in the equation of state plate. So this is something that the fact that that there will be at least 10 or more times pulsars discovered with SKA will definitely bring more sources and more things, more laboratory to test and measure masses, and hopefully radii or constraint on moment of inertia. I think this is it. This is it. Yes. Anna, do you want to add something to this?
No, it's perfect.
Okay.
Yeah, so Prakash asked a question and raised his hand. So I think this is good point to give him the mic.
Yes.
Yeah. Let me ask the second question first. There were reports that the currently known double pulsar system, one of the pulsars stopped pulsing. Has that changed?
This, I don't know the latest data, what they show, but I remember till a few years ago, and no, it's not pulsing at the moment, as far as I know. And this is a problem for the extrapolations. But I don't know if I don't know if Thankful or other radio pulsar astronomer can comment on this, on the latest result on this.
Okay, turning to the first question.
Yeah.
The ages on one of your plots were rather precisely shown. Is that really so? Are they as well known as the figure indicates?
No. So let me show. The answer is no, they are not that well known. So here you see, no, the ages are definitely, you see different colors in black and gray. Black sources are those for which, yes, the age error you can trust, because it's either a supernova remnant or a proper motion or the association with something else. Gray sources are those for which you have only characteristic ages. So let's say there are some of them that you can trust, some of them that's less.
So they're spin down ages.
Yes, the gray one, yes, they're all spin down ages.
Okay, thank you.
Nanda, maybe, yeah, I don't see very much what is gray and what is black. Can you say at least how many are black?
Really? Let me see if I can say it this way. Yeah, I didn't put it.
I see blue, I see gray, I see dark blue.
No, the numbers. Do you see the numbers? The names, sorry.
The names have to, okay.
Yes. So the colors are just the magnetic field. You see the label on the right.
Yeah, correct.
Are the names. The black names are those with good age measurement, which I would say it's maybe 20%, 30% maximum.
And you have them almost well distributed everywhere.
Yeah. So one of the things that we are trying to do is to compare some statistical analysis with those for which you know the age and those for which you don't, and see if the two things are consistent, to see how much we can trust the one that we don't. But this is work in progress at the moment. Yeah.
Thank you.
I have a question. Hi, it's Bruno. It's related to the table you showed before about the measure of the mass. In gravitational waves, you put in spiral plus kilonova question mark. What are you thinking in that case?
So there are limits, for example, on maximum masses, right?
Ah, maximum mass, okay.
Let me say, I consider that very orange, that kilonova statement, and I'm happy to argue with someone about that if necessary. But listening to Ben's very nice talk on Monday, for example. But yeah, it was the maximum mass.
Maximum, okay, thanks.
So David.
Yeah, just to clarify a little bit, the resonant shattering flares, I think they're actually probably, our last paper just showed that it's mostly the crustal composition at the base of the crust that you're going to be probing. More specifically, it's the shear speed, which is dependent on composition. So rather than, I mean, there is a dependence on mass and radius, but it's kind of orthogonal to some of the other stuff.
You mean you're with the time delay, or with the luminosity of it?
No, with just the timing, the timing. But you need it has to be multi-messenger. Yeah.
Okay.
Okay, so Anna and Nanda, so about tidal deformability, you were questioning whether it should be green or another color. So do you want to comment more about that? Or, I mean, how can we really state something from a single event, or should we wait for having more?
I think my question is, I mean, I guess we're very aware basically of the various modeling assumptions and so on that go into the X-ray, which is possibly why Nanda and I are labeling everything as being orange rather than green. And I would say some of them are more green than orange, perhaps. I mean, there are different degrees of modeling uncertainty, I think, that go into these various different things in the X-ray column. And I guess the question is, yes, do we have too much faith in our gravitational wave colleagues? Because there are, I think, waveform uncertainties right in there as well, and template uncertainties. And maybe if the gravitational wave folks had made this plot, they might be listing things a bit more orange as well. And we're all very nice about the radio pulsar folks.
Radio pulsars, no problem there. But I mean, I think at least you could, so it's not that there are no systematics. It's just that so far with the observations we've had, the statistical errors have been larger. So I don't know what color choice that implies. It's just a matter of time, I hope.
Well, I would call it, because also, for example, the moment of inertia with radio pulsar, this is if it's just a matter of time, I would call it green, right? But I don't know.
Yeah, I mean, I would hope to see a lot of these X-ray ones going green, basically, particularly once we can start to cross-check the different techniques against each other. I mean, we're starting to do that now with archival data as well, of doing what we can with what we've got left over, for example, from RxTE, again, to try and cross-check these different techniques. So we should hopefully already be starting to get a handle on some of this stuff.
I want the observers to react to what I'm going to say just now. If I think about the love numbers, which is intimately related with the tidal deformability, they drop as a function of increasing mass. So that means that unless the signal to noise ratio of very heavy objects is very large, in other words, it occurs very close to us, it will be rather difficult to get a reliable tidal deformability. I'm making a provocative statement. So could the observers comment on that?
I mean, certainly that already came into 1904-25, which had higher masses.
I'm more or less right.
Yeah, so since let's see, since the thing you're trying to measure becomes a smaller effect for high mass systems, it is harder to measure there. Yes, so I think the near maximum mass stars will be very challenging to get precision tidal deformability on. Yeah,
so the tidal deformability should be mostly centered around the canonical masses of 1.4 solar masses.
If you're looking for a measurement and not an upper limit, for sure.
Okay, thanks.
Which is going to make actually the JO437 measurement, when we finish the analysis, really interesting, because that one we know it's 1.4 solar mass for NICER. You know, we have like a 3% constraint now from our radio pulsar colleagues that we're using. And it will be really intriguing to see where that one lines up.
Maybe we can comment, I mean, if there are no other questions, we can comment on the temperature maps that we were discussing with Anna, derived by NICER somehow, which, how this, I mean, if there is any thought, any modeling on this.
So there's a lot going on. So I think one of the really nice things that's come out is the interest in the pulsar theory community, basically in kind of the surface maps that are coming, at least from the NICER modeling. So we've had some really good discussions with people about, yeah, can we try and, we need to link it up with the multi-messenger emission, or multi-waveband emissions. So link it to the gamma ray, link it to the radio, make sure it's all consistent, and try and tie it together then with kind of theoretical models of what's possible in terms of field configurations. And he said, you know, right now we just take a huge range of possibilities. We're looking at also sensitivities to things like temperature gradients as well, of whether or not that's an issue. So I think there's plenty of room for interaction there, because I think if you go back, for example, to our 0030 results, you know, the result that we reported was, you know, the most likely of all the models that we looked at. But if you look at kind of objective measures of model quality, you know, were there obvious problems in residuals when we use, for example, some of the simpler models? Not particularly. So I wouldn't die in a ditch if pulsar theorists come back at some point and say, look, you just can't have these crazy arcs. So far they haven't, that's all fine. But if someone came back at some point and said, you just can't have that, it's not allowed, you know, you have to go back and do something simpler. I think we could still produce a model that looks okay, but it might cause the radius to move a bit. For OSM 40, actually, we tested sensitivity and it wasn't an issue. It really didn't make a difference if we use different surface pattern models. So that's kind of quite reassuring, but that may change as we get better data on that source as well. So I think there's now room basically to say to the pulsar theorists, this is something we can test, it's input that we need. And that will be true for the accreting stars as well, of having a good handle perhaps on what the possible range of surface patterns are. And then asking, you know, having an interaction to and fro of whether our results are sensible in terms of surface maps as well. And I think there are already, you know, there's already been some studies that's shown that it's not crazy for 0030 what we came up with. It can also explain the radio and the gamma ray. That's great and really reassuring. And I think that interaction will come and go further as well.
Well, I can see from the chat that this table created a lot of discussion about the colors and things like that. I think this table that you have made is interesting, is indeed very interesting. And I was just wondering whether next time we meet all together, this might be the starting point of the workshop, just to start with a table like that, and just to continue discussing about, I mean, what we think about what you have assigned as a color, or what you think as a good candidate, or the good ways to measure properties of neutron stars.
Actually, one of the things that we were discussing to do, but it was definitely not doable in a few days, or something that needs months probably, is to add to each of those sections somehow a percentage of accuracy that we expect in that with that technique. And this somehow this needs more time and more thought, of course. And it's something probably interesting also to discuss in a meeting and do it somehow discussion, because there are a lot of things, for example, at least in my side from the gravitational wave point of view, that I just don't know. So it's good to do it in a community somehow. And it might be useful also to see where to, if we see which are the precision and the that we can get from all these different methods, we can somehow tune our observations. We can tune where to go to search for what is best to go to search for what. And I think it might be useful.
Yeah.
Then as a to-do list, Anna. We can do it.
And I see that Manu wants to add one more column and wants to put optical on here as well. I don't know if Manu wants to make a quick comment on that.
Yeah. Hello. Can I?
On a neutron star chart, that's horrifying.
Yeah, that's right. So, I mean, it's very interesting discussion, and I just missed this little optical side. and this part of the maximum mass of a neutron star, right? Which I think was mentioned by Cole a couple of days ago. And in particular, these spiders, these redbacks and black widows have shown already evidence for supermassive neutron stars. And that is something we're pursuing now. And actually, some part that is often missed is, of course, there's healthy skepticism towards these systematics, and the main systematics is on the orbital inclination of these models of the binary millisecond pulsars. But this new population of nearby spiders, we're now able to observe it with large optical telescopes, and we're able to beat these systematics in new ways. So one of the ways is measuring different spectral lines across the whole surface of the companion star. So, you know, that's really promising, and there's been, I think, little discussion of this as far as I've seen. I've missed some parts, but I just wanted to raise that point as well.
Yeah, that's a good point. We might add further column with the optical. Yes. Would you make it green, orange, or red?
I'm glad somebody is talking about colors. These are all very pastel. So could you make it, you know, gold, silver, and things like that? Gold plated, I would say, is radio pulsar timing.
This is relaxing, this color scheme.
Yeah, I mean, I'm not sure what the definitions of these colors are exactly, but in terms of the maximum mass, I would bet a dinner that in the next 5 to 10 years, we're gonna get closer to the 2.5 solar mass range. So, you know,
you're a troublemaker.
Yes, I am.
I love troublemakers, so it keeps me, you know, on my toes.
I'll take you on that one, Manu. 2.3 tops.
I've already told Scott Ransom that he should discover a 2.4 solar mass star. A long time ago, in fact.
I'm also fine with a 1500 kilohertz pulsar. Also, this I'm okay with that. We can find one. It's a millisecond one. Anyway. Maybe one of the things, if there is still time, that I was thinking while doing and filling up the slides, which was not much mentioned. So I wanted to ask why and which are the consequences somehow, is the minimum mass. So which are actually of course, from an observational point of view, this is harder to detect, a very low mass one, because you never know if it's a white dwarf or not. So it's difficult, but let's say which are actually the constraint that we can put and say if we detect a very low mass one.
Well, Nanda, if I may add on your point, I like to have a very low mass and associated radius.
Yeah.
Because somehow, in a way, I mean, low mass neutron stars are certainly the one that could validate the nuclear physics part of the modeling and tell us whether we are on the right track or if we are already at 2 times saturation density of what nuclear physics tells us. Because everything we say at higher masses, we never know whether there's already a phase transition, there are already something more than nuclear physics, but at least for 1.1 or maybe 1.2 solar mass neutron star, it would be hard to really be far from what nuclear physics predict, unless nuclear physics is totally wrong.
Yeah, that's interesting. And I would maybe expect this to come from gravitational waves rather than.
Yeah, or maybe nicer.
Not because they are not, because they are difficult to measure and detect in radio and X-ray.
Yeah. What about nicer?
maybe if, again, they haven't accreted enough during the recycling phase to push the mass up. I mean, Wynne might remember this, but I think that the lowest one, the one for which we know the mass for the nicer analysis, the lowest one is 1.4, unless Wynne remembers one of the masses for the other ones is lower.
1.17, no? Excuse me. It was another question.
For the nicer sources that we're measuring. Some of them we have known masses, but I think 0437 is the one with the lowest mass of all the masses that we know in advance, unless you happen to infer a low mass for a star where we don't have the mass constraint independently. But I think we have like a 1.6 and a 1.9, basically, and I don't think there is anything below 1.4. And again, you know, but maybe you luck out if one of the ones we don't have a mass constraint ahead of time, we end up inferring a low mass.
So someone asked in the chat what the lowest neutron star mass ever observed. Prakash say 1.1.
Accurately.
I think so, yeah.
I had in mind 1.17, but maybe I'm old-fashioned.
Well,
yeah, 1.17 say.
I think the table Jim and I constructed had 1.1 as being accurately measured.
Okay, if you have the reference, that would be nice.
Oh, I have to dig up a long time ago.
I've just dropped in a link for Paolo's webpage where I think he keeps a fairly updated list.
Yeah, that'd be a good idea. I don't know if Jim is still updating it, but somebody else might be. It could be 1.174. So don't take me to task on that one.
I mean, Chuck Horowitz did this very nice paper, right, on low mass neutron stars a while back, but I don't know what the latest status of that is.
Well, somebody asked what is the lowest mass theoretically. Theoretically, it is 0.8 solar masses.
You mean without interaction, the original TOV prediction?
Correct, because for most equations of state around that that mass, it is mostly most of them hover around 0.8 solar masses. Hover around.
Okay, good. Well, I think we had a very nice discussion. It's maybe, unless there are any additional and important question to ask to Anna and to Nanda, I would like to thank you very much for your contribution to the discussion. And
thanks a lot.
And then I will ask the two next person, Tim Dietrich and David Radice, to continue the discussion about gravitational waves and simulations.
Hello. Yeah, thank you. First of all, thank you for having us here and for organizing this workshop. It has been very interesting. So the way Tim and I decided to go about this is we prepare some slides mostly to kind of have a common ground and as a baseline for discussion that I'm going to share. And we tentatively decided to split this discussion in two parts. One more focused on gravitational wave uncertainties and modeling that Tim is going to lead, and one more focused on multi-messenger constraints. Do you see my slides now that I go to full screen?
Yeah.
Okay, so I think I will then leave Tim to discuss the first part.
Yeah, thanks a lot, David. So the good thing is that it was already pointed out by Anna that there is, of course, also modeling uncertainty in gravitational wave astronomy. And there was already a nice debate, and I hope that we can go into some more details. Of course, as for all Bayesian studies, you need relative precise theoretical models for extracting information from the data. We all know this. I just want to highlight two key points, namely that binary neutron star signals in gravitational waves are much longer than binary black hole ones. So this is a computational challenge. And second, that you have a higher dimensionality because you have tidal deformabilities and so on. So in principle, modeling black hole neutron stars or binary neutron star systems is or can be seen as potentially more challenging. Of course, people might disagree, which would also be nice for a discussion. But if we go to the next slide, here's an overview about what we have so far. And I don't want to go into the details, but it's important to realize or to point out that there are indeed different techniques, really different techniques that are cross-connected to model gravitational waves and get gravitational waveform models and then extract information from the data. On the one hand, we have numerical relativity simulations. I have put them on the bottom left because the issue is here that we will never be able to simulate a full signal from 2 neutron stars with numerical relativity simulations. It's simply too costly. We have to solve complicated PDE system, which if we, for example, once we computed it, would compute the gravitational wave signal from GW17817, this would roughly need 10 to 100 years on a supercomputer to compute the full waveform. Of course, the uncertainty then at the end will be very large. So we are currently at a stage where we can model realistically and accurately the last, about 20 gravitational wave cycles. I meant 20 orbits. It's around 40 gravitational wave cycles. It's the longest NR simulation ever done so far with realistic and small uncertainties. On the other hand, on top we have post-Newtonian theory, analytic waveform, which by construction has a problem when things come close together and becomes inaccurate. But nevertheless, it's a very good cross-check. And then you can remap the post-Newtonian, this is an effective one-body problem, as we all know from our classical mechanics. Here, just as a relativistic problem, the potential the good, nice thing about the EOB model is that it's significantly more accurate when you compare it to numerical relativity simulations. And finally, it has a combination of everything in some phenomenological models. And I listed all the different models that exist there for binary neutron stars and black hole neutron stars on the right side. And the good thing is, and this is also something that Jocelyn pointed out, that so far, when one compares the different results for different waveform models, things agree and we are clearly dominated by statistical uncertainties. But if we go to the future, and this is shown on the next slide, and for example, here we have an injection study, assuming we would be 4 or 5 years into the future, and we would see GW17817 again. Maybe source is a little bit further away, so at 50 parsec. Then on the left side, you see a plot for the tidal deformability. Black line is injected value. And all these different waveform models, here just a case of 4 waveform models, would still agree in the terms of their statistical uncertainties, right? The injected value is still inside the 90% confidence interval, we would be happy. On the right side, you see the same chirp mass and so on for the system, the same equation of state, but for a larger mass ratio. And here you see that there are clearly degeneracies in extracting information from gravitational waves. And you clearly see that even for source in advanced LIGO, at 50 megaparsec, a single source would lead to the fact that systematics come into play and different waveform models predict different answers. Of course, this is a slight exaggeration because one knows some models are more accurate than the other one. There's a clear, or not a clear, but there is a hierarchy in the modeling. So for example, the post-Newtonian ones, which is shown blue here, it's expected that it actually moves to the left, but still we would get into trouble. Nevertheless, this is 4 or 5 years into the future. Therefore, the discussion by coloring maybe green to orange in the future. But for the Einstein telescope, and this is my last slide now, and we actually will be potentially dominated by systematics massively, because on the one hand, and this shows the left plot, is the number of sources, binary neutron star sources that you expect with the Einstein telescope to observe within 1 year. And while now we had GW17817 and 190425, it's the case that we will observe, and this is not an exaggeration, but a few 10 or 100,000 sources. And GW17817 had a signal-to-noise ratio of around 37, and we will see significantly more sources that are much, much louder. And obviously then systematics come into play, even for a single source, as shown on the first slide, or previous slide, but even more when you want to combine things. And therefore, the question that was raised is a very important one, namely that one is aware that also gravitational wave modeling comes with an uncertainty, a systematic uncertainty, but mostly for the future. And Sebastiano, in his talk on Monday, raised a nice point. This is my question for the discussion on the next slide, namely that systematic effects from comparing different waveform models seem to increase massively, and this is understood because the physics becomes harder at high frequencies. So therefore, his suggestion was that one could think about the possibility that one just analyzes the signal to a lower frequency, where systematics are better under control, and this reduces systematics, obviously, but on the other hand, it also reduces the potential for us to get information out of the gravitational wave signal, because tidal effects are strongest in the light inspiral. So if we drop this, then of course we would have a problem. And my idea would be that either, I mean, now everybody of you is asked, because I want to have a small poll, everybody who actually thinks that one should restrict gravitational wave studies to smaller frequency and neglect the last two orbits should write in the chat just a 1. And everybody who thinks that it would be still good to go to the higher frequencies because, okay, systematics might become dominant, but we want to extract most out of it, writes in the chat, 1 or 2. So 2 is to higher frequencies, 1 for lower frequencies. And then I think, I mean, we are, I don't know, 70 participants. So I would like to know what's the common sense. And then this hopefully opens up that some people bring up their opinion and justify their choice. So.
Thank you, Tim. Can you repeat again the question?
Yeah, the question for everybody is that if you're, I should have put it on the slide, but it just came to me while I'm talking. If you are, if you think one should restrict gravitational wave analysis to lower frequencies because this reduces systematic effects, then write a 1 into the chat. If you think you should go to the highest frequencies because this is our possibility that you get most information out of it, you should write a 2 in the chat. So I start. You see, we already have a nice starting point. And whoever wrote something, I would be very happy if you bring up the point why actually you go for the decisions that you made. To trigger the discussion. And then I have another question, but this can be answered later.
But can I comment here, Sebastian?
Sure, great.
I think it's not a well-posed question. I think this is source dependent. So if you have, I strongly believe that for GW17817, the correct thing to do is to accept a slightly larger uncertainty, which is not so large, in fact, for multi-messenger application, for example. It is essentially equivalent. Actually improves in some sense, it makes the radius estimate more robust and less systematic dependent. So I think in that case, it is a good strategy to allow a very, very small error, or if you want, larger confidence region. But that's not necessarily true for other events, right? So it is something that depends on the scenario, on how much information you think that there is at higher frequency. So how much you are willing to lose. That's the question, I think. And that's a question that depends on the scenario.
Okay, so this means that for high SNR, you would go for higher frequencies.
So one should evaluate, imagine that you have tomorrow with the current availability of analysis, the same approximate tomorrow. You have an event tomorrow at very high SNR. So you cannot hope to improve from one day to another the waveform models, and so you know that you will have systematics. But the observation has an extremely high SNR. So in that case, that observation needs to be studied at higher frequency, and one needs to assess for that particular event what's the actual spread between the different approximant and judge based on the result that one finds. I think in general, you cannot say I give up the critical information at high frequency just because I know that there might be systematics, right? Also, certain measure of systematic through injection are very rigorous, but other measure of systematics that don't use injection. So, for example, the accuracy criteria based on the faithfulness, those are only necessary conditions, so they not imply immediately that there are systematics. And that so based, for example, only on those faithfulnesses, one should, I think, perform the full analysis and evaluate on the results. So I think answering this question in general is not, I mean, it's not a very well posed question. The question is, if you are in certain condition, if you are on a certain scenario, then, for example, in my opinion, is much better to keep a systematic free result, which does not even affect multi-messenger estimate on the radius, except shifting it a bit, but it shifts on the right direction, by the way, in the sense that is more compatible with NICER, for example. On the other hand, if you have a very high SNR, I think one should push the analysis and really verify whether the different approximate gives a consistent result and to which level it is consistent.
Okay, cool. Now, I mean, of course, the question was provocative. I mean, I think everybody will vote here 1 and 2 or 1.5. You clearly have to do this on multiple frequencies. I just wanted to get and trigger the discussion. And thanks a lot. And anybody else on this point? Should we go to David or to the other question that is here? Any preference?
Maybe a question still related on the frequencies. There's a question about post-merger observation that requires observing above 1 kilohertz.
Mm-hmm.
But that requires either to be very lucky or to change a little bit the sensitivity of the detectors, no?
Yeah, I think in the current framework, to be very, very lucky. Yes, one has to be very close. One can try to tweak things in the detector a little bit, but not really creating a dip at the high frequency range. Of course, there are proposals for other detectors like the NEO detector in Australia that really focus on the high frequency part, but this is then a fully different story with a NEO detector and so on. With advanced LIGO, it will be very hard to see post-merger part and to really extract accurate information from it. Okay, but then I think I would hand over to David, because there was also a lot of discussion about the kilonova, and I think that he will.
Okay, yeah, and we'll also talk a little bit about the post-merger, so we can come back to this discussion. Okay. Oops, I skipped one slide. How do we go back in this? Okay. Yeah, I wanted to show this once again. I think Sebastiano also showed this in his talk the other day. But this is the timeline for a binary star merger from a spiral merger and post-merger. The thing that I want to emphasize really is that as you move from left to right, you're not also only moving in time, you're also going from a regime that is very well understood to things that are progressively less understood. And the reason for that is that at early times in the spiral, obviously the dynamics is just determined by gravitational waves. It's gravity, which we think we understand relatively well. As you go through merger, hydrodynamics start to become important. And on longer time scales, when gravitational wave emission starts to die off, about 10 to 20 milliseconds after merger, other effects come into play, and the viscosity due to MHD turbulence, neutrino cooling, all of these things become progressively more important on longer time scales. So as we move from left to right, we go more and more into uncertain regions of the evolution. And I think when we talk about multi-messenger constraints, it's very important to understand where in this diagram the information that we are extracting comes from. Because obviously when we talk about gravitational waves here, nowadays we're only talking about the in-spiral, maybe in the future we'll have the post-merger. But when we talk about electromagnetic counterpart, are we probing the merger phase? Are we probing the long-term evolution? Well, that depends very much on what kind of multi-messenger constraints you're looking at. And so I don't think it's fair to pile up all the multi-messenger analysis that has been done so far in the same category, because some things are more uncertain than others. And that is because some of the physics here is better understood and some of the physics here is much less understood. So what I'm going to do in the next couple of slides is I will emphasize those aspects of the electromagnetic emission that really are related to the merger phase, which is the phase of the evolution in the post-merger that we kind of hope to understand, in the sense that here everything is just hydrodynamics, and of course there are big uncertainties in the equation of state, but we can turn the problem around and say that the merger is sensitive to the equation of state, so take the equation of state as a given at the moment of modeling. And there are not big uncertainties at this point yet due to neutrino physics and turbulence and MHD turbulence that become important later on. So two important things that happen at merger. The first is that there is a bifurcation in what can possibly happen to the binary. Either you form a black hole immediately or you don't. And if you don't form a black hole immediately, you can still form a black hole within a few millisecond time scale. So within the phase of the evolution that we think we understand in simulations. And this really has key consequences for the electromagnetic counterpart. Then what also has important consequences for the electromagnetic counterparts is how long the remnant survives after this phase, if it survives. But this is something that is much more difficult to understand, and people have discussed in the previous days of the conference the difference between supramassive and hypermassive neutron star. And I will agree that this difference is completely arbitrary, and that we don't really know which remnants are short-lived and which remnants are long-lived. If we exclude those remnants that collapse very quickly after merger, and those we know are short-lived. So two things that happen at the time of merger. First is the ejection of matter. And here I want to emphasize the physics of matter ejection. For comparable mass ratio binaries, so in this diagram here that I stole from this paper by Tim Dietrich, everything that is below about 1.5 in mass ratio, I would consider comparable mass ratio binaries. And if you focus on soft equation of state like SLY that are consistent with recent observations, you see that the mass ejection does not really depend on the mass ratio very much. And this is because this ejection is mostly driven by shocks. And you can see it also here in this diagram where I show the density in one simulation and the outflow rate. Essentially, most of the ejecta comes out at this time here, corresponding to the time when the two stars have merged. Here they are merging, if we look at as a function of time. The density shoots up when we form a hypermassive neutron star, then the remnant bounces back. And at this point that the eject is launched. There is some confusion sometimes in the literature. People claim that the mass ejection is due to shocks formed at the time when the stars collide. This is not really true. The vast majority of the ejecta comes out at this time here if the remnant bounces back. If there is prompt black hole formation, the density just shoots up, there is no bounce, so the amount of ejecta is very small for comparable mass ratio binaries. For unequal mass binaries, there is another component that is due to tides. And this is present regardless of whether you form a black hole or not. So we have to be careful with that. Similarly, the disk mass that is formed after these mergers is very sensitive to the lifetime of the remnant. Again, for comparable mass ratio binaries, here the binaries with Q equal 1, what we see is that the matter that forms the accretion disk is actually expelled from the remnant. So what's happening is that as the stars are colliding and merging into each other, the two cores are displacing material that gets ejected and forms a disk. So it's a process that takes time, and the disk is formed as the remnant survives. As soon as the black hole formation occurs, first of all, a part of the disk can be immediately accreted. This is what happens with this blue binary here. And second, obviously, you cannot inject more mass into the disk. This is for comparable mass ratio binary. For high mass ratios, again, the situation is different because in this case, a large fraction of the disk is due to the tidal disruption of the secondary star. So the main message here is electromagnetic counterparts and also nucleosynthesis are very sensitive to merger dynamics. So what can we do with this? So what we can do with this is we can use the fact that the electromagnetic counterpart is very sensitive to whether or not you form a black hole immediately. For comparable mass ratio binary, this is the picture. If you form a black hole rapidly, and this does not mean necessarily prompt collapse, it also may mean one bounce, but still not enough time to form a massive disk. Then the amount of ejecta is typically very small, and one can confidently rule out these binaries. We can confidently rule them out as being possible explanations for GW17 less 17, because all of this material that would be needed to explain the kilonova is inside the black hole. So even though we cannot simulate what happens to these systems on long time scales, we do know very well that photons do not escape from black holes. So these binaries here are kind of ruled out. Refinement on this is what has been done in this paper by Bresky et al. And many other papers by other groups, including work by Tim Dietrich. As instead of just assuming comparable mass ratio, as we did here, and placing constraints on lambda just by eyeballing the plot, one can combine fees to numerical relativity data that also include the high mass ratio binaries and do a careful Bayesian analysis of the results. And this is very useful to constrain the tidal deformability of the binary from the soft end side. This is a collection of results that are all framed in terms of the radius of the 1.4 solar mass neutron star, and the current constraints seem to be converging. At least many of the groups are finding radii around 12 kilometers. I don't want to go into the details of how all of this analysis is done. I think this is something for the discussion. The other type of multi-messenger constraints that have been proposed have to do with the lifetime of the remnant, whether the remnant collapsed on short time scale, tens or hundreds of milliseconds, or survived for many seconds or minutes. And I will argue, and people are free to disagree, so I'm happy to make a statement that is not universally agreed upon, that knowing whether a remnant collapses or not on this time scale is very uncertain and has nothing to do with or little to do with the separation between supramassive and hypermassive limit. This is because we find in simulation cases of stars that are hypermassive. So according to this criteria, they should be collapsed into black holes, but that because of mass ejection end up losing sufficient amount of mass to possibly end up in this region of stable equilibria, so they could survive for a long time. And similarly, we can imagine a situation where a supramassive object loses pressure support due to neutrino effects or finite temperature or MHD effects and collapses to black holes. So we don't know that there is a sharp transitional region between supramassive, hypermassive neutron stars. So I think any constraint that has to do with the lifetime of the remnant, with how much energy, rotational energy of the remnant is coupled to the kilonova is a very uncertain, and I think it would not be honest to say that there are no uncertainties there. There are uncertainties also, of course, on constraints that deal with the kilonova ejection too. The last thing I want to comment on is the post-merger gravitational wave signal. This is something we have discussed a little bit. And here the main thing I would like to convey is that the post-merger signal is often discussed in terms of this peak frequency that we know correlates with properties of the binary during the in spiral, like the tidal deformability, the mass ratio. So there are universal relations that we could use to either predict the value of this peak frequency or as consistency check, because we can measure this quantity here from the in spiral waveform, compare it to the post-merger frequency, and make a consistency check for our theory. But there is more information than that in the post-merger. So for example, one thing that we proposed some time ago is that if we are able to measure the amplitude of the signal in the post-merger, then we can measure the binding energy of the hypermass neutron star, which will tell us more about the equational state at very high densities. Of course, these measurements are challenging, but they're not impossible, especially if we know the distance to the source from EM counterparts. So here, my main provocation is it's good to talk about F peak or F2 frequency in the post-merger, but we shouldn't forget that the waveform in the post-merger is not just one number. There is more to it, and I think future work should really look carefully at holistic interpretation and modeling of the post-merger signal. So this brings me to the question for this section, which is what do we believe about these multi-messenger constraints? How do we decide whether we trust or not, and at what level of these constraints? Of course, as we try to improve our measurements, we are also more and more susceptible to systematic uncertainties. And so what is the right level of precision that we should be aiming for? Other things that I would like to discuss is, again, what can we realistically learn from the post-merger gravitational wave signal? The only thing we can learn is that we can measure once again the tidal deformability of the neutron stars, but with much lower precision, then perhaps this is not that exciting. Of course, the post-merger signal should encode the equational state at much higher density than these spirals. But how do we go after that? And then, especially for the simulators in the audience, what are the dominant uncertainties in the simulations? What is most urgent? What should we work on first? And finally, for everybody who's not doing simulations, what is it you would like us to provide you? Because we can compute a lot of things, but what is really needed in the broader community from numerical simulations, apart from gravitational waveform, which we think are useful? So I don't know how you want to proceed here. I couldn't really follow the chat, but feel free to add questions to the chat or comments. But mostly the discussion I would like to start is which multi-messenger constraints do you believe, or do you believe any of them? Or should we just rely on gravitational wave data alone? And what is the feeling in the community?
Okay, thank you very much. That's very nice point to start the discussion with. Does anyone want to comment or react? So yeah, Prakash, start to answer.
Yeah, I'm not taking the questions in order, but post-merger signals are the only game in town to measure finite T and very high density physics. So there comes the rub at the same time, because there are several theoretical expectations. Different people do different treatments of the very same problem. So that could be a good science point, because for the in-spiraling thing, finite T is out of the game. High density is also out of the game simply because they haven't merged. And you only get to sample the densities that are in the cold stars. And as we learned, measuring the tidal deformabilities for very heavy neutron stars is going to be an iffy affair unless we are very lucky. It occurs very closely. So these are the two physics aspects that I see that at least I'll be able to contribute, or people like me will be able to contribute in terms of post-merger signals, which means that the people have to do a number of simulations with different equations of state, with fairly different treatments of this part of the equation of state. So let me stop there.
Okay, I would like to, yeah, I agree with what Prakash just said. One question I would like to turn to the gravitational wave observers is if we have a nearby event, maybe we have 3G, is it really true that it is more difficult to measure the tidal deformability of a two solar mass neutron star? Or is it more difficult to measure the post-merger signal? Because this is not obvious to me. Of course, I'm excited if we measure the post-merger signal, but it's not clear to me that since they are both very challenging measurements to make, it's not clear to me which of the two is actually more challenging.
That's a really good question. It's close, but I think you would still. I think the important point here is whenever we're considering what we learn from post-merger, we need to consider it paired with the in-spiral that precedes it. And,
yeah, this I agree.
And how the two phases are distinct. I maybe, and this is a gap in the way people have been looking at this.
Yeah, I guess if we have a very nearby, very massive binary neutron star system, we probably have no post-merger because they will form a black hole immediately. But that will give us a chance to measure the tidal deformability of a high mass neutron star in a way that is much less affected by possible systematic uncertainties of the post-merger.
Yeah, and I do think with 3G detectors, you will see tidal effects from also very massive neutron stars when they merge. So there are studies looking exactly at this, and it's pointed out that you can clearly distinguish black holes from binary neutron stars, very massive binary neutron stars, even if you have a prompt collapse scenario, which then means that with 3G, we are in the game even at normal distances. So there will be a few per year that you see that are very massive, and for which you also get tidal deformability constraints. But of course, this means that you get 3G. I think for advanced LIGO, the game is, again, a little bit on the, you have to be not extremely lucky, but a little bit lucky side. At least this is what I remembered, seeing some studies about it.
Here, Sebastiano. Yes, I also agree on this. So I think if you have 3G, you might have, precision of, I don't know, perhaps a few percent, perhaps 10% on the measurement of the reduced tidal parameter. So even if you have systematics, let's say twice this value, you would have a very, very precise measure of this value here, and you will know, you will have a strong constraint on, say, two solar mass star, assuming that you hit a two solar mass star, of course. So, but I think, modulo the astrophysical probability of measuring a binary with or merger with that mass, it is something that is within reach, in my opinion. I mean, of course, I didn't do any calculation, but it is something that seems plausible to do with, say, current technology or 30 years technology. By contrast, if you have a similar binary that gives you post-merger signal, with 3G, you still need only to detect the post-merger signal, you still need something like order 10 SNR at kilohertz frequencies. And this is not at all guaranteed that, that you will have it. And this is only for detection. So if you want then to make a measurement there, you need much more. You might be 20, 30 SNR. I mean, these are the values that allowed Bresky et al. to do a proof of principle analysis of this consistency of the F2 frequency, for example. this is extremely high SNR, and it's challenging already. It's also challenging for 3G. So I agree that with what has been said, that a measurement of in spiral measurement of high mass neutron star in a binary might be more easy or easier to do, or it's a closer target than doing full studies with remnant kilohertz gravitational waves. Yeah. And I'm not talking about detection. I'm really talking about analysis.
So I think I mean, we also agree that it's easier to detect massive binary neutron stars from the inspiral and get the tidal ephemeralities. But I think the picture is a little bit more optimistic for the post-merger part, even in 3G. So there have been other studies showing that you can do some stuff with an SNR of 10 in the post-merger. I mean, not super accurate, but you can. And given all the number of detections that you expect, I think there will be, I mean, the chances that you do a post-merger phase in 3G is, I mean, I would clearly bet a lot more on that you see some post-merger that you don't, just from population studies and so on. It seems more realistic.
I'm not talking about observing. I'm not talking about detection. I agree with this SNR10 about detection.
But I think the works by Caterina Sciaziano, for example, that you have, they did an SNR of 10 and could extract key frequencies from the post-merger, and also some studies by...
Yes, but if you look in detail in this work, in all these works, they all agree in some sense. It's true that you can infer the reduced tidal parameter, say from F2, and do an estimate, but this estimate is very uncertain. So carries very large sigmas because it's uncertain. So what you want to do in principle is not only to detect the post-merger or to reinfer the lambda with an accuracy that is 2 or 3 times the one that you have already inferred from the inspiral. But in principle, what you do in order to really prove this high temperature, high density regime that was mentioned before, is to actually do some kind of precise measurement on that particular part. Which means the easiest thing is to compare, for example, for the inspiral, but you cannot compare with the inspiral if you don't have sufficient accuracy. So this is what I'm saying. I mean, detection is interesting, can tell a lot of things, but if you really want to, if you say that there is new information regarding high temperature and high densities, and I want to extract it, I think that's significantly more challenges. And to my understanding, all the literature kind of agree. Then it depends what people write, but in the numbers, there's an agreement.
I agree, but I also think that SNR of 30 will happen once or twice a year, according to estimates right now in the post-merger phase with 3G.
This we hope.
Yeah, that's, I mean, given uncertainties and so on, but yeah.
Maybe we can also look at the chat, and there are some questions.
Yes, a question by Bruno. Yeah, I think the uncertainty in the ejecta mass are maybe a factor 2, 3 if you want to be conservative. But actually, the ejecta mass is not a dominant source of uncertainty in the Kilonova modeling. The uncertainties that come from nuclear physics, like heating rates, the composition, are actually dominant sources of uncertainty in the Kilonova modeling. So for many of the current applications to multi-messenger astronomy, the dynamical ejecta mass is not really the dominant factor. Of course, if we had more precise simulations, we would be able to leverage even more the current data. But at this point, I wouldn't say that simulations actually are the bottleneck. One thing that is dominant in the Kilonova is very uncertain, for example, is the fraction of the disk that is ejected at later times. So at the moment, the only thing that we can do is we can say that if everything falls inside of the black hole, those models are disfavored. If we had better models, we could also distinguish between different systems that in principle could potentially produce observations like GW17 or 17 and tell which of those are acceptable or not. But at the moment, we cannot do that. So all of the current constraints just rely on whether there is mass outside of the black hole or not. And that is quite robust.
Okay, thanks. I was asking because I remember you also show sometimes this plot about the ejecta we get in numerical simulation versus the ejecta masses that are supposed from GW17 and 17. So, for example, also saw the comment by Ben saying that nuclear physics can also, impact the ejecta masses, as you were saying. So that would probably also change the ejecta mass, right? Or...
Yeah, I think there are big uncertainties there. The good news is we can do already multi-message astronomy if we take into account these big uncertainties. They are not actually that terrible to deal with, but we have to be aware that there are these uncertainties. In other words, the target requirement for numerical relativity simulation is an accuracy at the level of a factor 2 or 3 in the dynamical ejecta mass. And I think we are at that level of accuracy. Even if we compare simulations by different groups, they are at this level of agreement. If we want to do more, then we need to improve the simulations. But
David, just to be a bit of a devil's advocate, I agree that probably factor 2 of 3 sounds reasonable, but there has been work showing that changes in the nuclear physics can affect heating rates by an order of magnitude, and that could change presumably ejecta masses by an order of magnitude, which would be quite dramatic.
I fully agree with you. What I was trying to say is that the dominant source of uncertainty is not in the simulation. So it's the dominant source of uncertainty, as you say, is in the nuclear physics in the kilonova modeling. So depending on what you do there, you can change the estimate by quite a lot. And so in order to derive these electromagnetic constraints, what we try to do is we try to take the most conservative values from the literature. And again, we could do much better if we had this nuclear physics under control. But that's more urgent to fix, but it's, in some sense, it's something out of my league, fixing the nuclear physics of the kilonova. I only worry about the simulation part.
Okay, Jocelyn, you sent an image. Do you want to comment on it, or?
Oh, yeah, sorry. So this was, someone was asking what you would learn from or when you might potentially be able to distinguish the component tidal deformabilities. So this was an example of a plot of the component tidal deformabilities in a third generation sort of 2030s and beyond error gravitational wave observation.
Great.
Okay, if there is a if there is a minute, I wanted to go back to this discussion, the post-merger, mostly because we talked about detectability and doing data analysis, and the issue is that most of the work focused really on extracting this peak frequency, and there are these universal relations that are, in a sense, both a blessing and a curse for us, because the blessing is we know what to expect for this frequency. The curse is that if we measure this frequency, we don't learn necessarily anything new, because we just measure again with much lower precision the spiral parameters, because this psi is just a combination of the reduced tidal deformability of the binary and the mass ratio. So in order to really learn from the post-merger, we need to do more than just look at the peak frequency.
So David, do you have some phase transitions model in this plot, or?
We don't have, but we have done some work with a student at Penn State and collaborators, some of which I see here in the chat, in the channel. And we have added the phase transition runs in this plot. And what we find is that there are differences due to phase transition. So there is some information hidden in this scatter around the central value of the fit, but the delta frequencies are very small. So they are within the uncertainty of the fit. So you will not be able to tell a phase transition, at least the phase transition that we implemented, with just a change in the hadronic part of the equation state.
Because
so
I remember I think a similar plot by Andreas Bausen with maybe a first order phase transition where he showed...
Yeah, we also did first order phase transition, a slightly different implementation. There are two differences. First of all, the delta frequency we find is much smaller than what he found in his simulations. And second, he shows always the universal relation for a fixed equal mass system. So if you assume that you know the mass of the system, it is equal mass of 1.4, 1.4, then you can make a much more tight fit. While this includes systems that have very different mass ratios, very different total masses. So this is really a universal relation. In that case, it shows a relation that only includes systems for which you know precisely the total mass and the mass ratio. So in that case, you can get a more precise fit, and then the phase transition may stand out more. But if you don't know with infinite precision the total mass of the binary and the mass ratio, then you are back to this kind of universal relation that accounts for everything. But this intrinsic scatter in this relation is larger than the effect of first order phase transition, at least of the first order phase transition we implemented. There may be other cases in which it is larger, but again, not seeing a deviation from this fit does not necessarily rule out a phase transition.
Okay, good. Well, I think I'll have to maybe close the session. Of course, it's pretty disappointing because I like to stay much more with you, everybody. So thank you very much for participating to this virtual meeting.
All the attendees and all the speakers and discussion leaders for joining our meeting and making it so nice. Thanks. I hope to see you next time in Trento.
Yeah, thank you very much. Bye-bye.
Thank you all.
Thank you. Bye-bye.
Bye. Bye-bye.